Okay, so I'd like to welcome everybody to another edition of Quantum Computation and Isolation. So today I'm very happy to introduce Professor Anne Broadbent. So Professor Broadbent got her bachelor's degree in mathematics, combinatorics, and optimization from the University of Waterloo in 2002. She got a PhD from Université de Montréal in 2008. She was named a CIFAR Global Scholar and NSERC Postdoctoral Fellow at the Institute for Quantum Computing in the Department of Combinatorics and Optimization at the University of Waterloo from 2008 to 2013. She's currently an associate professor in the Department of Math and Statistics at the University of Ottawa. She is also currently holds the University of Ottawa University Research Chair in Quantum Information Processing. She's cross-appointed to the University of Ottawa Department of Physics, and she's the member of the Institut Transdisciplinaire d'Information Quantique. She is also affiliate of the Perimeter Institute and Institute for Quantum Computing. She is the recipient of numerous awards and prizes, including the University of Ottawa Young Researcher of the Year Award in 2019, the Ontario Early Researcher Award in 2016, the Andre Eisenstadt Prize in Mathematics in 2016, the John Charles Poliani Prize in 2010, and NSERC Doctoral Prize in 2009. And today she'll be talking about secure software leasing without assumptions. So please help me in welcoming either by unmuting yourselves and clapping or by clapping virtually, Professor Anne Broadbent.
Thanks for that nice introduction. It's a pleasure to be here. It's nice to see some familiar names and faces and also some new people. So I'm looking forward to more interaction. Please feel free to ask some questions. Joshua will be moderating that. When I accepted to give a talk in the isolation seminar, I did not expect that literally I'd be under isolation giving this talk. We're starting the third wave of COVID here in Ottawa, and my children's school is partially closed. So we're kind of locked down, and I apologize ahead of time if one of my youngest collaborators barges in and asks a question during this talk. This is joint work with Stacey Jeffrey, Sebastien Lord, Suparto Potter, and Arti Sundaram, and I want to thank both Stacey and Sebastien for their generous help in preparing these slides. The starting point of this talk is the well-known no cloning theorem, according to which it's not possible in general to make a copy of an unknown quantum state. This phenomenon is credited for many of the feats of quantum cryptography. It's actually embodied in different types of related theorems like the uncertainty relations, etc. So that's the starting point of our talk. We want to talk about making things unclonable. So for me, quantum information is more like a physical object, like an apple, if you want. This is something that you can taste the apple, but you'll leave a mark on the apple. It's going to change the apple. You could share the apple with a friend, but each of you can only get part of the apple. You can't both have the apple. So for me, quantum information is like that. It's something that can take advantage of these benefits in the physical world, yet we have a digital representation of quantum information in ways to prepare it and encode it. So that's the general idea. Actually, this idea of quantum unclonability was first presented by Stephen Wiesner in the very early stages of the development of quantum information. This was before the term qubit was coined, even before we knew about the no cloning theorem. Stephen Wiesner suggested that we could use quantum encodings in a way that would prepare unclonable quantum money, or if you wish, quantum tokens, or also sometimes called quantum coins. So this is a way that the authenticity of a physical object, and namely of these quantum coins, can be verified. And by the quantum properties, it's not possible to duplicate these coins. The proof of impossibility came many years later. And this original proposal was this idea of quantum encodings. But authenticity is just one level of unclonability. It doesn't contain any actual information. What would that be? What would that mean to talk about unclonable information? That question was asked by Gottesman as early as 2003 in something called Uncloneable Encryption. Here we have an actual message. So it's think about it as an email or something, and we want to encode it using quantum information such that only one recipient can decode it, meaning that it's not possible for two recipients to simultaneously, these two, to simultaneously be able to open the information and view it. So that's a higher level in the hierarchy of unclonability, if you will, in terms of encoding information. The previous one was an authenticated object. Next level higher is information. Okay, so what would be another level of this unclonability hierarchy? Well, the next level up is unclonable software, or if you will, an unclonable functionality. Here, we talk about the possibility of being able to evaluate a piece of software. Sometimes I call it a circuit, a function, a program. These are all related concepts that I kind of conflate. So here we would want to encode into a piece of quantum software, a functionality, and we would want to inherently prevent this piece of quantum software from being copied. So this concept was first put forward by Aronson in 2009, and this is going to be the focus of this talk. So this idea of making functionalities unclonable, software unclonable. And before going on, I want to emphasize that all of these concepts, unclonable authenticity, uncloneable encryption, unclonable functionality, they cannot be achieved using classical information alone. If you have a classical encoding, it's always possible to copy it simply by making a photocopy or a digital copy. And so this idea of preventing this type of splitting, you're never going to be able to do that. So these concepts are completely foreign if you're thinking purely in a classical world. However, they make a lot of sense in the physical world, like a physical object, a physical safe, an envelope that you close, a lock, things like that. You can try to get intuition from physical objects. Here, of course, we're going to be talking about quantum encodings that will realize this. Okay, so a little bit more detail. What do we mean by quantum copy protection? Okay, we talked about taking a function and putting it into some sort of piece of quantum software, which will be a quantum state together with instructions on how to interpret that state. So this is a quantum computer. You can think about it as a quantum interpreter, and it would take the piece of software and it would take the input X. This is the classical inputs, because for now we're talking about classical functions, classical inputs, classical outputs, classical functions. There's a prescribed method that combines the software with the input X in order to produce f of X. So that's the correctness of the quantum copy protection that we would want. And then security. Well, here we'll imagine a pirate, also called a freeloader, who is given a copy of this copy protected software. So the pirate could evaluate it honestly, just as in the prior slide. Or, as all pirates try to do, he could try to make a copy. So here he would want to make two possibly pirated pieces of software such that users, Alice and Bob, could simultaneously evaluate this function. So security means that they should not be able to simultaneously evaluate F. And that's what we're trying to ensure if we want to have a copy protected scheme. So I want to emphasize, if this were a classical piece of software, the pirate could make two copies. Alice would get a copy, Bob would get a copy, they could both run it. So that's impossible to realize classically. Quantumly, there's hope because of this concept of no cloning. So if we want to talk a little bit in more detail of what this means, how are we going to formalize this? So if we're doing cryptography, we want to give like a security definition. In that case, you trying to think about what this means and how you can formalize it, you immediately come up with the question of, what does it mean to have a functionality? What does it mean for Alice to be able to evaluate a function? And what does it mean for Bob to be able to evaluate a function? How are we going to quantify that? Because we want to limit that capacity that they're both able to evaluate the function. And one way to quantify that is to give these users, or these potentially malicious users, to give them challenges. So we'll ask Alice to compute the function on a challenge input, and we'll ask Bob to compute the function on a challenge input, and then we'll evaluate how good they are at both simultaneously computing that function based on these challenges. So to be more concrete, we'll talk about the specific families of functions that we want to look at. And that will be point functions. Why do we choose point functions? Okay, actually, what's a point function first? A point function is a map from n bits to single bits. And they're special because there's a single point p that maps to 1, and all the other points evaluate to 0. And why do we choose point functions? Well, point functions are a pretty simple class of functions to express. They're parameterized only by the point p. And so the relatively simple class, this is a hard problem, quantum copy protection, so any progress is good. Next, we actually know that learnable functions cannot be copy protected. This is a rather straightforward result. A learnable function means that using polynomial number of queries to the function, it's possible to reconstruct the entire function to learn which function it is. So if a pirate can learn the function, assuming that this is a learnable function, then he knows what the function is, and he can give that description to both of the other parties who are trying to two parties who are trying to evaluate this function. So he can basically copy it. So point functions are not learnable, and they're one of the simplest classes of functions that are not learnable. For a point function, it's easy to express what it means to be able to evaluate the function. Namely, we can give a challenge p and check the answer. And a little bit later, we'll talk about how these point functions in terms of copy protection can be extended to a slightly larger class called compute and compare. I'll tell you about that later. So now we specify our definition of quantum copy protection for point functions in particular. So we have this distribution here. With probability 1/2, the input x will be chosen to be the actual point. And with complementary probability, the input x will be chosen to be one of the other points, one of the other 2 to the n minus 1 points. So in terms of correctness, we'll ask that up to some error term eta, the outcome is correct. The outcome here of evaluating f sub p on input x is correct in expectation over this choice of x. So this is the correctness definition. There's no security right now. It's just saying that if we have a scheme that we want to claim it to be copy protection, it better work correctly. And this is how we're going to evaluate this correctness. It's average, and there is a better definition of correctness that we could hope to achieve, and that would be worst case correctness. So for all points, you would want to have some correctness up to eta. And we'll talk a little bit later about the limitation of this type of definition here of average correctness. In terms of security, now we have this point function that we're talking about. So I've already hinted that we'll be giving challenges to Alice and Bob. We'll be asking her for a choice of point x1, we'll be asking her what is this function evaluated on x1. By the way, she doesn't know p, of course, like that's the important part, right? And then we'll be asking Bob a different x, we'll call it x2, and we'll say what is f on that value x2, and he'll give an answer. Okay, so again, we'll use the same challenge distribution. And then we'll say that Alice and Bob win if both Alice and Bob are correct. So Alice outputs the correct value, Bob outputs the correct value. And we'll say that the protocol has epsilon security if the probability of winning is upper bounded by 1/2 plus epsilon. Where does 1/2 come from? Well, 1/2 is the probability that they would win if they guess randomly in a coordinated fashion. So they would uniformly at random, they guess They both guess 0 or they both guess 1. And that wins with probability 1/2 because of the challenge distribution. With probability 1/2, we've chosen xi equals p. And with probability 1/2, we've chosen the other one. And then the epsilon is a little fudge factor that we allow ourselves. This definition can be generalized to other functions and challenge distributions, but for our purposes today, we'll be talking about this one. Feel free to ask any questions while we're discussing. Okay, so the first observation is that quantum software is reusable up to a certain point. Okay, so here's my illustration of how you could reuse quantum software. And note that there's a distinction here between reusing and copy protection. Copy protection is about simultaneously being able to have Alice and Bob being able to evaluate it. Reusing is a single person at their location trying to evaluate the software multiple times, one after the other. So suppose you had a quantum software encoding with the quantum machine that evaluates f sub p of x. And for this part of the argument, suppose that you make this evaluation pure. Okay, that means that you're not going to do any measurements. You're going to do everything. Another word is coherent. We're going to do everything in a unitary fashion. So when you have the output, we can do a control not here to copy the output. It'll be in the computational basis, and we'll copy the output here. And then we will undo, that's why there's this arrow in the other direction here. We will run the purified process in the other direction. And this will effectively undo the original process, which was to evaluate. And then the claim is that we will, via that process, we will obtain the original copy of the software up to some minor modification due to the correctness error. So the claim is that eta correctness of the scheme, meaning that the f sub p of x is correct up to some eta, will imply that the output program over here is order eta close to the original program. So that's just to emphasize that quantum software is reusable. So we're going to be talking about using it once, but really it's possible to reuse it using this process. Okay, so exploring this world of quantum copy protection, what else could we say? These are relatively straightforward claims. So first of all, I already mentioned this, learnable functions cannot be copy protected. And the reason I said was that it would be possible for the polynomial time pirate to simply learn the function, and that becomes a classical description of the function, and then he can share that with Alice and Bob. The next one is a little bit less straightforward, but suppose that we have the perfect correctness, eta is equal to 0. So in the prior slide, when we talked about quantum software being reusable, what you would do is that actually that process would perfectly recreate the original quantum program by running the unitary version, copying, and then undoing the unitary. And that means that in case of an unbounded adversary, who has infinite computational time, he'll be able to generate the entire truth table of this quantum software and therefore make it classical. And he'll be able to share that with Alice and Bob. So we cannot have quantum copy protection with perfect correctness if we're claiming security against unbounded adversaries. I wanted to review a little bit what we know about quantum copy protection. Aronson introduced the topic, and he showed that all functions that are not learnable, so all the ones that we can hope to copy protect, we can actually copy protect, assuming a quantum oracle. An oracle means it's an idealized version of an obfuscated software program. An oracle means that a user has access to a functionality that by definition, they cannot reverse engineer it. They can only have access to that functionality via the input and output behavior of that functionality. So this work assumed a quantum oracle, which is a relatively strong assumption, and the quantum oracle had was related to the program that you wanted to make into a copy protected program. This was improved very recently to a classical oracle, which again was also related to the function that you wanted to turn into a copy protected function. And also in the last year, it was shown that all compute and compare functions can be quantum copy protected, assuming what's called a quantum random oracle. And this is a stronger result because it weakens the assumption. The assumption of a quantum random oracle by nature means that this oracle is not related to the function that you want to turn into a copy protected function. This is an idealized version of a function that is random. Really, like you give it an input, it gives you a random output. And that's it. And then I mentioned compute and compare. This is a generalization of point functions. And compute and compare, the way to see it is that it uses a point P and a function G. And to evaluate this compute and compare function, you should first evaluate G on your input X and compare that to P. And if that's equal to P, then you should output 1 and you should output 0 otherwise. And they actually showed a way to go from compute and compare to a copy protection for point functions to copy protection for compute and compare functions, which I'll tell you about shortly. Our result on quantum copy protection is for point functions by the prior work that extends to compute and compare functions. We introduced a new adversarial model for the evaluation of the security, and we call it honest-malicious, meaning that the first evaluator, Alice, will be honest. So she is running the regular evaluation procedure of this copy protected software, whereas the second evaluator, Bob, is fully malicious, and he could be doing any type of operation in order to evaluate this function. So this is a definition that's kind of halfway in between perfectly honest and fully malicious evaluation. And the justification is that we could have devices such as in terms of a set-top box, for instance, if you're thinking about some sort of premium video service, you can think about a smart card that is running some trusted software that's embedded in the device. So that would be the honest evaluation. And then the freeloader, or Bob the pirate, is running some rogue hardware that's trying to take advantage of any type of side information that could be created by the pirate. And then we have no other assumption. Oops. We actually have no other assumption, so there's no random oracle, there's no computational assumption, etc. So a quick sanity check, it means that since it'll be necessary to have some error parameter, otherwise by the previous slide, we cannot have perfect security. But otherwise, there's no other impossibility result. But this is kind of very close to the known impossibility results, but we just managed to skirt that by having some small error parameter that will prevent the brute force attack that we talked about in the previous slide. Looking ahead, we're going to show how to implement honest malicious copy protection using what's called quantum message authentication codes. But first, I want to tell you about the sequence of the results that this copy protection is going to enable. So the title of my talk was Secure Software Leasing. We haven't actually talked about that yet. We talked about quantum copy protection because this is the core of the technical result is quantum copy protection in this honest malicious model. So bear with me for some more definitions. I'm sure you'll find them interesting. So secure software leasing, this is related to quantum copy protection, but slightly different. So we imagine Alice, who is a software vendor and wants to lease software, meaning that there is a time frame after which the software should be returned. So we actually count here on on the pirate to actually return the software. Maybe there could be penalties or something if it's not returned. But for now, we'll just say that the pirate is going to comply and return something. Alice should have a way to verify that the software is correctly returned. And when it's returned, it should be impossible for the pirate to be able to evaluate the function afterwards. So after the software is returned. So this is really, again, something that's not possible classically. Classically, you could always keep a backup copy of the software, and there's no way to prove that you haven't kept that backup copy. It's different quantumly. We'll show that we can actually implement this type of software leasing. Now I want to draw the same picture, but in different positions. So imagine here that, again, we have the software that's created here, and we will make these two blue disks here correspond. So imagine that the Alice is either in the secure software leasing picture, she's sending this one, or in this other picture, she's creating this one here. It goes to the pirate. And then in the secure software releasing, the purple one here is the pirate returning the software to Alice for verification so that she can verify that it's returned. Here on the right-hand side, instead we relate to this honest malicious copy protection. Here we look at the honest Alice evaluating the software. The observation is that one way of verifying that software is returned is to actually evaluate it and check that it still works. And so we actually have this correspondence between honest malicious quantum copy protection on the right-hand side. So this is HM copy protection. And on the left-hand side, this SSL that we're trying to describe. The remaining system, the green one here, is whatever the pirate has tried to keep as a potential backup copy, and here is whatever the second evaluator Bob has in the honest malicious copy protection setting. So the observation is that if we have honest malicious copy protection, then there's a way to turn that into secure software leasing by defining the verification procedure as being the honest evaluation. And that we can actually write as a theorem. So honest malicious copy protection implies SSL. Hence, that's why the honest malicious copy protection is such an important building block in the paper, in the work that I want to tell you about today. In terms of software leasing, this was an idea very recently proposed by Ananth and LaPlaca, and they showed impossibility of secure software leasing for general functions. So meaning that there's a specific class of functions for which it's not possible to create an SSL encoding under some assumptions such as LWE. And homomorphic and quantum fully homomorphic encryption. And then they showed a possibility result, and that's the one we're going to focus on today. So they showed a construction for SSL for compute and compare once more. Here they assumed honest evaluators. So that would be that this pirate would be honest here. No, this one would be honest. That's for this Ananth and LaPlaca result. And then making a bunch of other assumptions, quantum secure subspace obfuscators, a common reference string, and the difficulty of learning with errors. But nonetheless, that was the first kind of possibility result for secure software leasing. This was also studied in the same year by Coladangelo, Magins, and Paremba. And they showed SSL for compute and compare, assuming a quantum random oracle. So once more, this is an oracle that's unrelated, necessarily unrelated to the piece of software that you're trying to obfuscate. And so it's a relatively weaker assumption compared to the other ones. And this was for a, there's no computational assumption in this work. And also the model of SSL was for dishonest evaluations. And also in the same year, we had SSL against honest evaluators. And here, this should be seen as an improvement of the original work by Ananth and LaPlaca. So here, the assumption was standard assumptions, namely learning with errors, and that's it. So what do we do? How does that fit in this picture? Well, we're going to do secure software leasing for compute and compare functions with average correctness and no assumptions at all. No random oracle, no computational assumptions, no common reference string. Okay. How do all the results fit together? So that's what I want to go through right now. We have this construction. So we're going to go from quantum total authentication, which is here. We're going to show how this implies honest, malicious, average case, copy protection for point functions. And then that will imply secure software leasing of compute and compare with average case correctness. And then actually we know of such existence of quantum authentication codes. So that means that the entire chain is actually realized and we can go all the way to the right-hand side. There's another related result that I want to touch on briefly. It's that, okay, so what about this average correctness business? Could we improve that? And we weren't able to improve it for our actual scheme. However, we were able to show that if we had a malicious copy protection for point functions, so that would be for the more general definition of both evaluators being malicious. And if that is only shown to be average correct, then there's a way to transform that into a fully correct, so that's worst case, correct copy protection for point functions, also malicious. So this is kind of saying, well, okay, we weren't able to go all the way, but if you're able to do this step, then you'll get the final result that we were hoping to get. And then since we don't know, like right now, there's still a question mark whether we can actually do this one. So we also don't know precisely how to do the right-hand side on the bottom part of the slide. Compute and compare functions. I've already mentioned this, touched on this briefly. We, once more, we have this f sub p with function g. And the output is 1 if you evaluate g on x, and then you compare that to p, and then you get equality. And a lemma from prior work is that SSL for point functions implies SSL for compute and compare functions. So therefore, if we restrict ourselves to point functions, we'll automatically get compute and compare functions. And the idea is that this function g that's used in the evaluation over here, we could give that in the clear as in terms of the encoding or for quantum encoding. And so we give that as part of the program. And then we'll use the point function secure software leasing on this f sub p of x. So now we've converted this into a point function only. This comparison here to compare whether, see here we see this implicit point function is to compare g of x with p. So that's the one that we encode using our point function secure software leasing. Yeah. And in order to evaluate this compute compare function, as suggested above, we'll first evaluate g of x and then use the secure software leasing to compare with the other function. So my screen has gone blank. Let me just troubleshoot that.
On my side, I can still see compute and compare functions slide.
Okay. That's my. I'm gonna just pause the screen sharing. Okay, I'm back, I hope. Sorry, that was just a technical issue. Can I get a thumbs up? Is that okay now, Joshua?
Yeah, I can see it shows a slide that says compute and compare functions again.
Okay. Yeah, the intuition is that knowing g of x does not help a pirate if they don't have access to f sub p of x. So for now on, we're going to focus on secure software leasing for point functions only. That's going to imply compute and compare. Okay, so going back to the screen of a summary of results, to which we'll return many often. So now we have this implication here. And we will therefore focus on this one here, which will be the major part here of this technical contribution. How we can go from quantum message authentication to honest, malicious, average, correct, copy protected point functions. What's quantum message authentication? So this is a way to encode a message. It could be a quantum message or a classical message into a quantum state. And importantly, the encoding is a quantum state such that a pirate will be detected. A pirate changing the message. Here we have M tilde. So if M tilde becomes the new message, then the recipient will be able to detect this. This is a keyed system. There's a private key here shared between Alice and Bob that will enable them to detect this. And the honest evaluation with no interference by the pirate will be accepted by Bob, of course. And there's a version of quantum authentication called quantum total authentication, which is of interest here. And it has a stronger security guarantee. It guarantees that the side information held by the pirate in case of Bob accepting, so notice here that the message is not changed and Bob is honest, that side information has nothing to do with the message or with the key. So that's a key, sorry for the pun, to this concept that we're going to be using here, this quantum total authentication. How could we, okay, so a little bit more details. Technically, what does the quantum authentication look like, and in particular in terms of quantum total authentication? So this is the real world where you actually have the attack map. This is the pirate doing the attack map, and the key K here. So a classical key K is chosen, the message is authenticated, it goes through this attack channel, and then the message is verified. And then we talk about this row KRL, which is this combination of the message and the auxiliary register after the conditioned actually on acceptance, because the var K prime is conditioned on acceptance. In the ideal world, we picture an authentication, and then importantly, there's an attack channel here that acts only on the quantum side information. So that's independent of the message and independent of the key. And then we talk about this resulting state row K ideal, also conditioned on acceptance. And the security is that we have this approximate equality here that which essentially guarantees that these remaining states, row K in the real and row K in the ideal, are close. And once more, this depicts the fact that the side information held by the pirate in the real world would be independent of the key. And we have ways to realize these total quantum authentication schemes, either using by two designs or what's called the strong trap code. How are we going to make quantum copy protection from quantum message authentication? So here's the link, and here's kind of the trick. It's a different way to think about quantum message authentication. We are going to associate the point P with the key. So this auth sub P, this is the notation for the encoding procedure for the quantum authentication. Usually the subscript here is the key K, but now we're going to be using the point as the key to the authentication scheme. So we have a fixed state. It's basically, you can think about it as a dummy state. We don't really worry about the message at all. We worry about the key. So in order to encode or a copy protection function for the function f sub p, we will choose a dummy state and encode the dummy state using the key p. That means that somebody with the key can verify the authenticity, right? That's the definition of quantum message authentication. But that's related to the challenge that we have into verifying the correctness of the quantum copy protection that we're trying to create. So these are all related. Namely, the evaluation, when we want to evaluate, given a quantum copy protection for the function and a challenge point Q, we will run the verification using as key that challenge Q on the input sigma. And the outcome of the evaluation will be 1 if and only if this verification accepts. So by the correctness of the original authentication scheme, if we're running with the same point, P, we have the same point. Well, if you encode with the key K and then immediately decode by the correctness of the original authentication scheme, you should accept. And that same process is going to make the evaluation of the copy protection scheme output 1. So that's correct. That's if we have that's if we're trying to evaluate the point on the actual point that's encoded. But now if we have a challenge Q that's different from P, well, the chances that the outcome is 0, which is the correct outcome, right? If you're evaluating for Q different from P, then you should output 0. Well, we use the properties of the quantum authentication scheme, and I'm skipping some details here, that is the probability is pretty close to 1, which is good enough. And note that this is why we get this average case correctness, or this correctness in expectation. It's because of the properties of the quantum authentication scheme. We're only able to show this in expectation. Okay, so this is this top part of the slide reviews the actual scheme, and now let's talk about security. So clearly, we're going to inherit security from the security of the total quantum authentication scheme. And importantly, we talked about the register of the pirate conditioned on acceptance in the quantum total authentication scheme would be independent of K. And now, since K is the point, it means that when there's an honest evaluation that accepts, it means that automatically the pirate will have his register will be independent of the point. So therefore, whatever he does, hence, no matter how malicious he is, he won't be able to evaluate the point function. Okay, so how does that go? Well, we have the honest evaluator. If it correctly evaluates on the point, well, that's equivalent to accepting an authenticated state. And then we use the properties of the QAS, the authentication scheme. On acceptance, the attacker knows essentially nothing on the key. And well, that key is related to the function that we're trying to encode. And hence we can relate the attacker in the QAS scheme to the combination of the pirate and the malicious evaluator in the copy protection scheme. And if the honest evaluator is correct, then the malicious evaluator will know essentially nothing on P. So that's, again, when I mentioned the properties of the quantum total message authentication scheme. And therefore, we're able to bound the probability of winning as P guess. Okay, P guess is a half. This is a slightly more general presentation where we can talk about more different distributions, but for our purposes, it's a half. And then we get these parameters epsilon related that come from the quantum message authentication scheme. But essentially, this is close to a half. So that's what we were looking for the security of the honest malicious copy protection. So now we've established this part here. Okay, that was the biggest technical contribution, how to go from QAS scheme to honest malicious copy protection. And once more, we already have this one here. I wanted to touch a little bit more on the bottom one. I don't have a slide, but I want to just mention how we would do this. So to go from malicious, average correctness, the idea is that we can transform this into a fully correct scheme by using something called a pairwise independent permutation. And this somehow spreads out the error equally among all inputs. So the point of the average correctness is that we're not able to bound the error for specific inputs, but by using this extra construction of a pairwise independent permutation, it just kind of spreads out the error. And that means that we can get the worst case correctness. And because we're assuming malicious security, that's the important part of it. This proof only works for malicious security. It means that we can incorporate these permutations into the adversary's evaluation procedures, and therefore we can get the security of the initial scheme. So the initial scheme with the pairwise independent permutation will give this malicious fully correct copy protection for point functions. Okay, so now I can just review some questions that are left open. One would be standard correctness for a scheme, so to get rid of this average correctness. How about security of the copy protection against two malicious evaluators? I don't think, I haven't found a reason why it should not be secure. I think it's a limitation on on the proof techniques that we used of using QAS. So there could be other approaches that could show full security against two malicious evaluators. And if we solve this point 2, it will automatically solve point 1 by the observation that I had at the bottom of the previous slide. And then another question would be to do unconditional secure software leasing for functions beyond compute and compare. So with that, I want to thank you for your attention and thank our sponsors.
Okay, so if anybody has any questions, I think we have plenty of time. You can either unmute yourselves, you can raise your hand and I can unmute, and then you can unmute, or you can ask it in the chat. So maybe we'll wait a few seconds.
Sure, take your time.
So maybe you might have mentioned this a second ago, but you said unconditional secure software leasing for functions beyond compute. Well, okay, 2 questions. Unconditional software for functions beyond compute and compare. Maybe you can go into that a little bit more.
On what would be the possibilities there?
Yeah, so it'll be some of the possibilities. Yeah.
Yeah.
Mm-hmm.
Yeah, I don't know. It's it's kind of like a tightrope between the impossibility results. We know it's impossible in general. So to find what type of functions could you hope to achieve and how, it's a game of looking at the actual function and its properties.
Mm-hmm.
So yeah, I don't know what to say. Interesting question.
Yeah, because I guess that's sort of tied into my second question, right? Because I was going to say, well, beyond, I mean, computer compare functions are generalization of point functions, and I was going to say, what about beyond point functions? But then I guess that sort of is the same question then. Mm-hmm.
Yeah, not up to date, but I would try to get inspiration from classical obfuscation. And so what are the functionalities that can be obfuscated classically, and try to see if that can be lifted to quantum, where maybe the classical schemes can be used as subroutines, and that can help to kind of bootstrap whatever you're able to get quantumly.
Mm-hmm. Okay. Any other questions? So maybe I'll wait about 5 to 7 seconds in case anybody wants to unmute.
There's a question in the chat. Joshua, do you have a way to collect slides, or should I contact this person directly?
I don't see it, so it might be just to you.
Oh, it's private. Okay. Yeah, so somebody's asking about sharing slides. Is this, do you have this already as arranged, or I could just email this person?
Yeah, so if you, 1 second, Chu and this person. So I actually have a mailing list I'm going to put in the chat. So Professor Broadbent, if you want later on today or whenever it's convenient, you can just email me your slides and then I can send it to the group.
The group, okay.
Yeah. Okay. Sorry, I can't, I must have been a direct message.
Yeah, I didn't notice, thanks.
Okay. Yes, there's one question. You may unmute.
Great. Thanks so much for the talk. I do have a question. So with the honest malicious, you said there's no assumptions, right? If we extend to malicious, would there still be no assumptions, or we need to set something now?
Yeah, I think it's definitely possible to look at this for malicious without adding any extra assumptions. I don't think that's necessarily required. Adding assumptions could be a step if the proof seems to be difficult to attain, but I don't see any fundamental reason why it would be required.
Perfect. Thanks.
Okay. Any other questions? So maybe, like I said, I'll wait 5 or 7 seconds in case anybody wants to unmute. Okay, so let's maybe thank Professor Broadbent again.
Thanks again. It's a pleasure.
Thank you.